Hello, my name is Robert Smith, and I'm with New River Community College's Academic Assistants, and today we are discussing atomic orbitals. And I have two small problems here that we're just going to kind of go through and discuss some of the concepts because this is a very conceptual section. So we're asked to list the values of the NL and ML for orbitals in the 5D subshell. So when you're talking about NL and ML, this N is your principal quantum number. And that generally is given by the period, which if you were to, let's make a little drawing over here. If you were to look at the periodic table of elements, it kind of looks like this terrible drawing, but that's the rough shape that it looks like. Each row is a period. So period 1, 2, 3, and so on, all the way down to 7. So looking for clues, you'll find that the 5 in 5D subshell is going to be your principal quantum number. So N is equal to 5. Okay. So the next thing we're looking for is L. And L is our what's called the angular momentum quantum number. And it's often referred to as a subshell, whereas N is referred to as a shell, L is referred to as a subshell. So we can again look at what clues we're given here. We're given 5D. We determined that 5 is the principal quantum number, so D must be our angular momentum quantum number. Now, what do we do with that? Because it's a quantum number, not a quantum letter. Well, 0 is your s orbital quantum number. It's a s subshell. P is denoted as 1, and D is denoted as 2, and F is denoted as 3. We know from our that L from your textbook must be less than N, but greater than or equal to 0, and it must be an integer. Must be a whole number. So, in looking at this, we know that L can only be 4, 3, 2, 1, or 0. And the D indicate in the 5D subshell indicates that L must be 2. Again, S is denoted as 0, P is denoted as 1, D is denoted as 2, and F is denoted as 3. So now you're wondering, what about 4? Well, 4 would be this theoretical subshell that has not yet occurred and may occur if we ever get into an 8th period. But essentially what it would be is this could extend beyond, but it needs to be, we need to get to those future elements first. So this is just a framework to guide us. The next thing we're looking for is M sub L, and that's our magnetic quantum number. Now note that the question that we're asked to find all the values for orbitals in the 5D subshell. That means that they want us to find multiple orbitals, and you can conceive of M sub L as being your orbitals, whereas L is your subshell, N is your shell, M sub L would be your orbital. Okay, so in looking at that, we know from our text that m sub L is going to be equal to all numbers in the set of from L through 0 all the way to negative L. So it can be any of those. And in looking at that, we just need to work through each one because we're asked to do multiple orbitals. So now that we have all the information that we need, let's just go ahead and list out all the possible m sub L orbitals with their n and L. So we could do a chart where we have n, L, and m sub L. And in this chart, we would have n is 5, L is 2, ML is 2. N is 5, L is 2, ML is 1. N is 5, L is 2, ML is 0. Extend down this chart a little bit more. N is 5, L is 2, ML is negative 1, and N is 5, L is 2, and ML is negative 2. So that's it for listing all the values for NL and M sub L. We could also do M sub S theoretically, which would be the spin quantum number. And all it would be is it would just double the number of entries in our chart, where each entry would also have a plus 1/2 or a minus 1/2. But we are not asked to do that, so let's just skip that step. Our next question asks us what the total number of orbitals associated with the principal quantum number n equals 4. So what can we do? We can make a chart, or we can use the simpler method if we're asked for the total number of orbitals associated with it. We can simply use the method that n to the second power is going to equal the number of orbitals. Okay, and with m sub L being our number of orbitals. So in doing this, we can just look at what's 4 squared. It's 16. But let me prove this to you. We're going to go ahead and do the chart just so that you can prove to yourself that you can see that this in fact holds true. Now you have to be careful with it, because if you're asking for the total number of orbitals, this works perfectly fine. But if it's asking for the total number of electrons, you're going to have to multiply this value here by 2 to get the total number of electrons. Now, if they're asking for the total number of subshells, or this simply would not work. And you could just use simple arithmetic to find the number of subshells. But this right here gives you the number of orbitals. So be wary of the word usage, because they could just as easily have asked for the number of electrons. And if they did that, if it was the number of electrons, you would put a 2 in front of that to get your total number of electrons. So let's go ahead and construct a chart to prove to ourselves, to convince ourselves that this is in fact the proper method and a correct method to determine the total number of orbitals. Remember, the number of orbitals is our m sub L. So we've got n L and M sub L. So we've got when N is 4 and L is 3, M sub L could be 3. When N is 4 and L is 3, M sub L could be 2. When N is 4, L is 3, M sub L could be 1, and so on. When you go through each of these, might need to carry this down just a wee bit. Now we're finally in when L is 2. I know this is quite a long chart. But we're just convincing ourselves that the equation that we used previously is an accurate equation. Let's go in reverse here. Okay, so we've done all the possible permutations of this. So let's count them up. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, which is exactly what we got when we used our much simpler equation. So definitely keep that equation in mind whenever this comes up on an exam. It's a very quick calculation, and you won't have to worry about what exactly, making a chart or anything like that with your N, L, and M sub L. That way it saves you precious minutes on an exam, and it's just as accurate. And in fact, probably more so because you won't be likely to make a mistake if you're doing a simple calculation rather than tabulating an entire chart. That's all we have for today on atomic orbitals. And they're not very difficult. It's just a matter of wrapping your mind around the concepts behind them.